All right, friends, we're talking about Math 105, and we're making a second video for section 5.1, and we're just going to do some problems together. But I wrote out our properties of logarithm just so that we have them available to us while we are going through this problem set. And I think the first problem set should probably be something that we know and love. Let's take an exponential. How about y is equal to 3,000 times 1.07 to the t. And the story here is that a population starts at 3,000 and grows by 7% each year. And we'll say, in what year exactly will the population hit, let's say, 5,200 individuals? So I think it's pretty clear that we're going to start out by setting 5,200 equal to 3,000 times 1.07 raised to the t. And now I know that you're eyeballing this bottom property here, but I want you to notice that if I put both sides of this equation into log, I'm going to have to do some manipulation here, that I'm going to have 3,000 times this mess, and I would have to use this second property to get it done. So I think that the key in doing many of these problems is isolating your exponential if you can. So if I isolate, I'm going to divide by 3,000. So we'll have 5,200 over 3,000 is equal to 1.07 raised to the t. Now both sides are going to go into log, yeah? I'm going to put log of this entire side and log of that entire side, and make sure that you're using parentheses here. The log of 5,200 over 3,000 is equal to the log of this trash, 1.07 raised to the t. Notice that that t is inside the parentheses, yeah? And so now the t can come forth, and I'm left with the log of 1.07 is equal to the log of 5,200 over 3,000. And you could reduce that if you cared, but I don't. And we're going to finish up by dividing by this constant. And so we'll have the log of 5,200 over 3,000 divided by the log of 1.07, and that is equal to t. If I want to, I can put this into an adding machine and get a decimal approximation, but this is a perfect answer that I expect you to be able to write on your exams and on your online assessments. Let's do a couple manipulation problems now. And so I want us to simplify the following. What about log of 100 raised to the x? And if we look at this, I think we can certainly employ this bottom property, yes? That I have log of something raised to the t power, and we could rewrite this as x times the log of 100. But I think we can keep going. And the reason I think we can keep going is that 100, I could express that as log of 10 squared. Yay, nay? And so by having the log of 10 squared, I can see that we're really using this inverse property, and murder will occur, and we'll be left with 2 times x. Let's do a couple more of these simplification problems, and maybe we can look at something like, what about 10,000 raised to the log of x? Now, we're somehow in a world of hurt because I can't use this property. It's not 10 raised to the log of x. And so what I might do is I might recognize that 10,000 is the same as 10 to the fourth. And we're looking at 10 to the fourth raised to the log of x. Now, friends of mathematics, you must know your properties of exponents, yes? And so our exponent properties say that the 4 and the log x multiply together. 10 raised to the 4 times log x. And that's all good and fine, but I cannot use this property yet because I have the 4 in front of the log, and can we use a property to maybe bring that 4 inside of the log? And the answer is sure. Sure we can. We can use this property, but in reverse. We can rewrite this as 10 to the log of x to the 4th power. And now I have my inverse that I'm raising 10 to the log, and we can just write this as x to the 4th. Pretty exciting stuff, yes? Let's do one more of these types of things. What about something like the log of 3 times 10 to the x? And if I was going to try to manipulate this thing down to the best way I possibly could, I think the first thing that I would have to say is that, that x is not going to come down because I'm not raising the entire argument to the x power. And so I'm going to have to use that second property of log, the log of a product. And so we can have the log of 3 plus the log of 10 to the x, at which point I think log of 3 is going to be untouchable. But log of 10 to the x, we have a function composed with its inverse, and so we have just x surviving, and that would be our final answer. We're going to do a couple more problems, and then we're going to call it a day. Let's have some population. P of t is equal to 2.5.8 raised to the t minus 4. And what this says is in the 4th year, the population was 2.5 and it's decreasing by 80%. And let's say, when is P of t going to be equal to 1 exactly? So we can set this equal. We can say 1 is equal to 2.5 raised to the 0.8 to the t minus 4. But, I'm sorry, that shouldn't be there. It should be here. And, I think isolating our exponential is usually a very good idea. So hence, isolate exponential before logs. So we do this. I'll divide. We'll have 1 over 2.5 is equal to 0.8 raised to the t minus 4. I'm going to apply logarithm to both sides. Log of 1 over 2.5 is equal to log of 0.8 raised to the t minus 4. Notice that our parentheses here, I guess these parentheses are kind of redundant, in that I know that I'm raising 0.8 to this whole thing, but here I got to make sure that that exponent is inside of log, because otherwise I cannot bring the thing down. And so now the exponent can come down, t minus 4 log of 0.8. And we're just going to start solving for t. There are some of you that want to distribute this, but I think that's a waste of life because log of 0.8 is just a number. Log of 1 over 2.5 divided by the log of 0.8 is equal to t minus 4. And to wrap this thing in a tux, what are we going to do? We're going to add 4 to both sides. Log 1 over 2.5 over the log of 0.8 plus 4 is equal to t. And we're out. Let's go again. Let's do a different problem. And this time I want to have a log problem, not an exponential. Now, I know that you might not like it, but we'll have 3 times the log of 2t plus 1 is equal to 7. And we want to solve for t. Exactly. So, you know, I could exponentiate both sides, but that's typically a bad idea right now because I don't have logarithm isolated. So, just like before, we isolated exponential before taking the log. Let's isolate our log before exponentiating. So I'll divide by 3 and we'll have the log of 2t plus 1 is equal to 7/3. And now I'm going to exponentiate both sides in order to use my inverse function to get rid of logarithm. 10 to the log of 2t plus 1, 10 raised to the 7/3 power. Here, murder occurs. We're left with 2t plus 1. And we could also say, no, murder occurs, right? That this is the inverse function composition, 10 raised to the 7/3 power. And at this point, I think we have a one-stepper. T is equal to 10 to the 7/3 minus 1, all of which is divided by 2. Let's do one last problem here. One last problem. And I think this one, I don't know if it's harder or not. Let's say we have the log of 6 plus the log of x squared. And let's say that equals 19. And we want to solve for x. So I think that there's some people that want to exponentiate immediately, but to do that, you would have to know your properties of exponents. And so the final thing that I'm going to say as far as hints are concerned, try to combine logs before exponentiating. Collapse into 1 before exponentiating. If we do that, I can combine these two because the log of a sum is equal to the log, or the sum of logs is equal to the log of a product. Log of 6 times x squared, yeah, is equal to 19. Now, I'm going to exponentiate both sides. 10 to the log of 6 times x squared is equal to 10 to the 19th power. Murder occurs. 6 times x squared is equal to 10 to the 19th. I'll divide by 6, and we'll take the square root, giving us a plus or minus. X is equal to plus or minus the square root of 10 to the 19th over 6. Mind you, that 6 is in, we divided that first. Okay, so there are log properties. Just make sure that you're going step by step, and you are not inventing anything new, and things will come correct, I promise.